Our next speaker will be Dr. Ryan Babbage from Google AI Quantum, and he will talk on demonstrating quantum algorithms for chemistry and optimization on these Google quantum machines. So please.
All right, thank you. Can you hear me okay?
Yeah.
All right, great. Yeah, so today I'm going to talk about two experiments that were performed using Google's quantum hardware. The references for the experiments are listed on this slide here. One of them I've given the archive reference. It's recently accepted in Nature Physics. The other we recently had accepted in Science. And both of these experiments are examples of quantum variational algorithms. So I think yesterday you heard a talk from Sergio Boixo, who was telling you about this experiment that the Google team demonstrated last fall, which was showing the first quantum computation which solved a problem which would have been classically intractable otherwise. So in some sense, I think one thing we learned from that experiment is that with the hardware we have in our lab today, we can prepare at least some extremely complex quantum states that you can't really access classically. But you know, that isn't equivalent to actually solving a useful task. And so, you know, one of the next logical questions is, how do we make states that are actually relevant for solving some sort of application that we might care about? And in the NISQ era, one of the most common answers to that question is to use a variational quantum algorithm. And so I think many people are familiar with this paradigm, but just briefly, a variational algorithm is, it's quite similar to sort of the way that a quantum neural network might work. So a neural network is a classical function which has some parameters and it realizes some probability distribution. And you usually want to adjust those parameters in order to make the probability distribution that it realizes match the probability distribution of, say, some data that you're interested in. So a quantum neural network is a very similar concept. The idea is that instead you have some parameterized quantum circuit. It prepares some state. You then evaluate some objective function on that state that tells you how close it is to a state that you might care about. And you use some classical optimization routine to update the parameters that characterize the circuit and the state. And I would say this is probably the most popular paradigm for solving problems, say, in chemistry and in optimization on near-term quantum devices. And so today I'm going to tell you about experiments that use this paradigm both for chemistry and for optimization. And we're going to start with the chemistry application. So in particular, often when we talk about solving quantum chemistry on quantum computers, we're actually talking about what's known as the molecular electronic structure problem. So the goal here is usually to compute what are referred to as molecular electronic energy surfaces. So on the right here, I've shown, in some sense, the simplest molecule. It's the hydrogen molecule. It has 2 protons and 2 electrons. These things are interacting with the Coulomb operator. They have kinetic energy, etc. And when we're talking about energy surface, we're usually talking about the nuclear energy surface. So that's sort of giving the energy of the entire molecule as a function of where the nuclei are. So in this case, there's only 2 nuclei, so there's only 1 coordinate that's describing the nuclear surface. So I could plot the energy of, you know, the energy of the ground state as a function of, say, how far apart the 2 protons are. And that's showing the binding curve here for hydrogen. And generally, we're quite interested in these energy surfaces because knowledge of them allows us to deduce how chemical reactions actually occur and also to predict rates of chemical processes. But often, especially for certain strongly correlated systems, obtaining these energy surfaces to high accuracy can be challenging classically due to the quantum nature of the wave functions. So the work I'm going to tell you about today was recently published in Science. I have a picture of the cover we got here. And so one of the things that we did was, in addition to showing one of the largest quantum chemistry quantum computations, we also perform the first quantum simulation that actually discriminates the correct pathway of a chemical reaction mechanism. So in telling you about this, I should probably start by telling you how we actually represent the problem on a quantum computer. And in general, whenever we're trying to represent a molecular wave function on a quantum computer or any computer, we need to discretize space. We need to confine the wave function to some basis. So when we're talking about molecular systems, a very common basis to use is the basis of molecular orbitals. These are single particle functions, and we basically build up the many-body wave function from antisymmetric products of these things. So the idea here is that we have one qubit, which represents one of these basis functions, which is referred to as a molecular orbital. And if the qubit is 0, that means there's no electrons there. If the qubit is 1, that means that there is an electron there. So in the example I've written out here, we have 2 electrons and we have 4 orbitals. And in general, the wave function is going to span a number of states, which is the number of orbitals, choose the number of electrons. So it's growing combinatorially in system size, which is one of the reasons that we need a quantum computer. So in particular, the variational algorithm we're going to describe is what's known as Hartree-Fock. So I'll get into that in a bit more detail. So again, it's a variational algorithm. We have this parameterized quantum circuit. We're using a classical optimizer to minimize the energy. But in particular, the parameterized quantum circuit that we're going to look at here has a very special structure. And the structure is that it corresponds to what we call a rotation of the orbital basis. So to be a bit more specific about that, if our initial state was a product state, and say the basis functions that I've drawn out here, the wave function is just a product of electrons in these orbitals, then after we apply this parameterized circuit, the new wave function is going to be an entangled state, but it could be written as a product state in a new basis, where the new basis is written as a linear combination of the old basis functions. And it turns out that there's prior work which has shown how to optimally compile such basis rotation circuits. And you can do this with, it has sort of a very nice structure. It turns out that you only need a quantum computer that has linear connectivity, and you can optimally realize this operation with circuits that are just linear depth. And furthermore, for the special case of basis rotations, if you optimize a wave function to if you optimize the basis rotation to get the wave function at the lowest energy, the wave function that you're preparing is the lowest energy mean field state, which is known in chemistry as the Hartree-Fock state. Now, the Hartree-Fock state is actually classically tractable to compute. And in fact, there's no advantage to computing it on a quantum computer, which you might think makes this a strange choice of experiment. Why do we do it? So there's a number of reasons for this, but to list a couple, basis rotations are really a ubiquitous primitive. They're sort of like the Fourier transform for quantum chemistry. They come up all over the place. They're a starting point for much more complicated methods that we might want to build from perturbatively. But they're also a subroutine of the most efficient, most performant algorithms, quantum algorithms that have been described for chemistry. Furthermore, the states that we prepare with these circuits, they actually are very entangled states. They have some sort of hidden tractable structure, but the quantum computer doesn't really know about that. And this makes them, in a number of ways, an excellent benchmark, but it also allows us some sort of deeper insights that allow us to better understand how errors are affecting the system. And as we'll see, that's very important for our experiment. So I'm now going to jump in and just show you a little bit of data, and then we'll talk a bit more about it. But first, I just want to say that the way that we collected this data is we used the Google Sycamore processor, which is a 54-qubit processor. And we compiled the circuits using OpenFermion and Circ. So both of those are open source frameworks. OpenFermion's an open source package for analyzing and compiling quantum algorithms for chemistry, and Circ is Google's API for programming quantum computers. And the circuits that we executed were these basis rotation circuits I mentioned before, and they turn out to have a structure that looks like what I've written here on the right. So, for example, this is a 12-qubit experiment. There's a bunch of 2-qubit gates in the pattern that I've written out here, where each of these 2-qubit gates can be decomposed, as I've written on the left here, into 2 square root I-swap entangling gates and 3 single qubit rotations. And it turns out this square I-swap gate is a native operation on our hardware. So that's how we realize these circuits. So just jumping into showing some of the data now. the smallest molecule we looked at was actually a 6-qubit example that corresponded to a chain of hydrogen atoms, the H6 system. And these hydrogen chains are sort of a common benchmark for quantum chemistry for a number of reasons. But the bond curves that we're showing here, it's showing the energy of the molecule as you change the distance between the hydrogens equally for each of the hydrogens. So this first data that I'm showing here, like I say, it was for H6. It was on 6 qubits, and this was already a bit larger than the largest prior quantum chemistry experiments, which is a bit surprising, you might think, because there have been a lot of experiments doing quantum chemistry on quantum computers, but a lot of people don't realize, due to the high precision required, thus far they've been limited to very small sizes. But we also did this for H8, H10, and H12. So this H12 example is now more than double the number of qubits and more than 10 times the number of gates as the largest prior experiments. So I've shown you some data here, but I haven't really described it at all. There's different colors. What does this mean? Let's take a little bit of a closer look. Okay, so first we'll focus on these yellow data points here. This is sort of the raw energies that we get out of the device when we're applying the variational ansatz. So there's no error mitigation strategies going on. The green dots, which are now lower energy than the yellow dots, are using a error mitigation strategy, which is fairly common. It's a very scalable strategy, which is post-selection on particle number. So the general idea here is that whenever we perform the measurements of the different correlators that determine the energy, we can also measure how many electrons are in the system. And in all of these chemical systems, we know how many electrons are supposed to be in the system. And so if we ever make a measurement and we see that there's more or fewer electrons than there's supposed to be, we know there was an error and we just discard the result. And immediately this improves the fidelity substantially, and that's a totally scalable procedure that we can always do. But we also developed a couple different error mitigation techniques in this experiment. The blue data, which is yet a bit improved over the green data, corresponds to another error mitigation technique, which we refer to as McWeeny purification. So I don't really have time to get into the details of this, but this is a technique that comes from the study of n-representability, which is sort of the study of the correct geometry of electron wave functions. And it turns out that there are certain relations between the correlation functions we're measuring. And so if we measure a set of them and we see that this set of correlation functions doesn't sort of correspond with itself the way that it's supposed to, there's a way of projecting it to the nearest set that does. And that's essentially what we're doing there. And then the red dots you can't really see in this image, but that's improved a bit over the blue dots from the variational algorithm actually correcting some systematic errors. So to kind of understand the contributions of these different methods, we can take a closer look at this. Here I'm showing, on the left, I'm showing the error in the energy as a function of bond distance. And you can see that we're getting, maybe half an order of magnitude or an order of magnitude improvement with each of these methods. And then on the right, we're actually able to, because of the special structure of the Hartree-Fock state, we're able to efficiently estimate a lower bound on the fidelity of the state that we're preparing. And so I'm actually plotting the an upper bound on the infidelity on the right here. And you can see how the different methods are improving the quality of the answer. And I also have shown the exact numbers estimated by this lower bound on the fidelity here. And what's remarkable is that even for the largest system studied here, which is involving 12 qubits and well over 100 2-qubit gates, with these error mitigation techniques, all of which are scalable, we're able to get over 99% fidelity, which is quite important because very high precision is required for these experiments. So I mentioned too that in this experiment, one of the interesting things is we are able to actually do a computation which allows us to discriminate competing chemical reaction mechanisms. And so another thing that we looked at here was the isomerization of the diazine molecule. So diazine is like hydrogen peroxide. It has 2 nitrogens and 2 hydrogens, and there's a double bond between the nitrogens. So it can either be in the cis isomer or the trans isomer, if the hydrogens on the same or opposite sides of the double bond. But because you can't rotate around a double bond, there's a question of sort of what's the mechanism of interconversion between these isomers. Either the hydrogen can rotate out of the plane, or it can rotate in the plane to do that. And what we're able to do is we're able to compute the energy of the system as a function of the nuclear coordinates for both this out of plane and in plane mechanism. And we're able to see what the lower energy pathway is, which allows us to discriminate the mechanism of the reaction. And in fact, we do have sufficient precision on our device to do this. So this is kind of a template for how one would really study chemical reaction mechanisms on quantum computers in the future, which, it's sort of well established how you would do this, but, it's the first time that we're able to look at something large enough to actually do that. I want to emphasize a technique that was developed on our team that really helped get the high performance in these experiments, which is something we refer to as floquet calibration. So the general form of the 2-qubit gates that are implemented natively on our architecture, we can write as a matrix, and it looks something like this, with a number of parameters, gamma, zeta, theta, and phi. And we have some idea of what these parameters are, but the reality is that they do drift a bit in time. And on average, this 2-qubit matrix is roughly the square root of I swap gate, at least the way that we're operating it in the experiment. But in fact, there are some small deviations from that. And as you can see, it's drifting in time. So in order to get sort of the highest fidelity calculations possible, it's important to develop a calibration technique for characterizing these drift parameters and correcting them as we're applying the circuits. So our team actually had a paper that came out on arXiv last night, which is mostly about an experiment that is simulating the time dynamics of the Fermi-Hubbard model, but there's a kind of extensive appendix in it which is describing this technique. And you should take a look at that, because this technique was also quite important for our Hartree-Fock experiment. But generally, the idea is that we're able to sort of characterize what these drift parameters are with some Heisenberg limited scaling by repeating these gates a number of times in a way that amplifies small changes in the eigenvalues of the unitary. So this is sort of a critical technique for us. And I should say that this is we got a lot of help with this. In fact, this technique was entirely developed by the physics team within Google's quantum computing team, which is led by Vadim Smeliansky. Okay, so I'm now going to move on to talking a little bit about doing a different type of variational algorithm on our hardware, which is a variational algorithm for solving optimization problems. So discrete optimization problems are everywhere, and solving these problems are very hard. So in this sense, it's a kind of ubiquitous application that many companies are interested in. And in fact, sort of the promise that quantum computers might, in some cases, be able to offer some advantage in optimization has driven a lot of interest in the field of quantum computing over the years. Although I would say it's still yet to be seen whether this is really a viable application, especially in the NISQ era. But here I'm going to tell you about our attempt to perform one of the most popular algorithms for NISQ optimization. So first, it's going to be a variational algorithm like before. And generally, when you're using variational algorithms to do optimization, the idea is you just are going to minimize the expectation value of the optimization cost function that you wish to optimize. So for example, we can think of any two-body or quadratic function of our bits, which is maybe the cost function we wish to optimize, as a graph. So to start with, our hardware is connected in a planar architecture. So in this experiment, we went up to 23 qubits. We have a 54-qubit chip, but we just used up the 23 qubits. And the 23 qubits are connected in a way that looks like this. So for example, if you happen to have an optimization problem that is connected in this way, then that would be very easy to implement on our hardware. But in reality, the optimization problems you probably care about, they probably have some different sort of connectivity. So for example, a common problem to look at, because there's a lot known about its complexity, is the Max-Cut problem on 3 regular graphs. And here's an example of a random 3 regular graph. But also you might be interested in even more highly connected models, like a the Sherrington-Kirkpatrick model, which is a model of spin glasses and has every bit connected to every other bit. So it has, n squared connections. So the algorithm, the structure of the variational algorithm we're going to apply is the quantum approximate optimization algorithm, which is probably the most popular algorithm for this purpose. And the way that this works is very simple. So you basically have repeated applications of this unitary u sub c and u sub b. So u sub c is just evolution under the cost function that we were just talking about. So these cost functions, for example. So for example, in the case of the Sherrington-Kirkpatrick model, evolution under this thing involves just applying all n squared of those edges, and it's a diagonal operator. And then this is followed by application of single qubit X rotations, all by the same parameter. And you repeat this sequence for a number of layers that's equal to p. The literature always just calls it p for some reason. I should say that the particular form of this u sub b operation is specific to QAOA. But basically, any algorithm, any optimization algorithm you could probably imagine performing on a NISQ device is probably going to involve something that's almost identical to this u sub c. You're probably going to have to phase the computational basis by some amount that's proportional to the cost function. And that's because that's sort of how the quantum computer ends up feeling the optimization problem that you're applying. And so while this study is specific to QAOA in some sense, I think we're also learning more broadly about how we can apply quantum optimization algorithms, because this u sub c is probably going to be the bottleneck for almost any quantum optimization algorithm that you would want to apply in NISQ. So we'll jump right in again and show you a little bit of data and then discuss it with some more context. We looked at a number of problems, our ability to optimize a number of different problem graphs here. And the first example we looked at was the simplest one for us, which is optimization problems that are just defined by the bits coupled with -1 or +1 couplings on the hardware connectivity that was native to our device. And so in fact, in most experiments where people study QAOA, they just apply it to their hardware graph because that's the easiest thing for them to do. Of course, real optimization problems don't tend to look like this, but it's still interesting to ask how well we perform when we do that. So when we apply just one layer of the algorithm, we can, as you see in this slide, there's two variational parameters, the things we're going to optimize. There's this gamma parameter and this beta parameter. And so if we just apply one layer of the algorithm, we can plot the energy surface as a function of those two parameters, beta and gamma. And here's a noiseless simulation that shows what it's supposed to look like. And here's a scan from our device. This is at 23 qubits. Showing experimentally what the energy landscape actually looks like, which is quite close. So it turns out the optimal solution is where I put this star here on the left. And so as an example, there was one experiment we performed where we initialized the system at this red square, and we performed the classical optimization, and it eventually converged to the red circle, which is the correct solution. So everything seems to be working well there. However, ultimately, in many cases, people are probably interested in solving much more challenging optimization problems, ones with a much higher degree of connectivity between the bits. Optimization problems are connected more like this, but it's quite a challenge to realize an optimization problem that looks like this when your hardware is only connected, much more sparsely with something that looks like the bottom one here. But it is possible to do this, and we do this. We do it using a swap network technique. So it turns out that it's possible with only linear connectivity in your chip. You don't even need to use the planar connectivity. You can optimally compile a fully connected graph into a circuit of n depth, where in each layer things are fully parallelized. So you're applying n/2 gates in each layer. And basically, each of these purple 2-qubit interactions here corresponds to simulating both the edge of the optimization graph and then also applying a swap gate, which we can compile into our architecture using 3 native entangling gates and 8 single qubit gates. So that's a lot of gates, but we're able to do it. So now I'm going to show data from a fully connected model. This one is only at 12 qubits. And you can see the experiment is still sort of qualitatively capturing the features of the landscape, but it's, it's obviously a bit more challenging because these circuits are much, much larger. Nonetheless, at this size, we're still able to perform the classical optimization, and it is able to ultimately converge to the right solution. So we might wonder, though, how is this actually scaling with size? So for the hardware graph, we see some behavior that might surprise you a bit at first, but if you think about it, it's not so surprising, which is that, so what I'm going to plot here, it's the approximation ratio we're able to achieve. So a higher approximation ratio is better, and this corresponds to the quality of the solution that you're able to find. So first we'll focus on the blue squares here, and this is showing a numerical simulation of, if you didn't have any noise, how well does the QAOA algorithm work for the hardware graph as a function of the number of qubits. And we're looking at a number of different instances here, but the largest instances here have, almost 202 qubit gates. And what's kind of interesting is that, and then the circles here show the experimental data. And what's kind of interesting here is that essentially the quality of the solution levels off and doesn't decrease past a certain point. So that's kind of encouraging, actually, in a sense, because it seems like the algorithm is not getting worse with system size. And naively, you might think, well, the circuits are getting much bigger, so shouldn't the performance get worse? But it turns out that because the cost function is entirely local, and the circuit to realize this is actually of constant depth, you can kind of predict this theoretically, and it's maybe not so surprising. I should point out here that this approximation ratio of 1 would be perfect, and even in theory that's not achievable except for the smallest problem sizes. If you get an approximation ratio of 0, though, that means your quantum computer really isn't working. That would be as good as random guessing. And so if you get to 0, that means it's not working very well. All right, so now let's take a look at the data for the Sherrington-Kirkpatrick model. So here we're looking at much, much larger circuits because we have to do all this compilation. Even though it's an optimal compilation for any architecture, there's still a huge amount of overhead because this thing has, n squared edges. And so you just need at least n squared gates, and that's a lot of gates. And in particular, we have well over 1,000 2-qubit gates for the largest sizes studied here. And we see that while theoretically, if you didn't have noise in your circuits whatsoever, this would, the performance would sort of level out. In practice, experimentally, it does start to get worse as a function of system size. Okay, so the last thing I want to show you here is the scaling of this algorithm with the depth of the circuits. And in particular, in QAOA, in a noiseless study, you expect the optimization ratio to get better as a function of system size. But in experiment, there's noise, so that doesn't always happen. In fact, in almost all prior experiments, you see it strictly get worse. In our experiment, we actually see that the performance does peak at about 3 layers of the algorithm, so it does get better up to a point. And on a per instance basis, we see that as well. So it's the first time that behavior is observed. But it's ultimately still going to get worse because of noise. Okay, so I'm now going to essentially conclude the talk here and just sort of overview what we've discussed. So we discussed the largest realization of a quantum chemistry experiment with good results up to 12 qubits in the first discrimination of a chemical reaction mechanism. And the ansatz we realized corresponded to a non-interacting fermion evolution, which is Hartree-Fock when optimized. But I think sort of the key results here were really more about error mitigation and how we can improve the performance by sort of being clever about different techniques there. We also discussed one of the largest, or the largest, optimization of a non-native hardware graph problem. And we saw the performance of the algorithm increase with depth for the first time. But still, I want to emphasize that we're quite far from doing anything in the classically intractable regime. And I think to get to that point, we probably need much better error mitigation, or perhaps we just need error correction, which is a real possibility. And error-corrected devices are probably a long ways off. So we're going to have smaller NIST devices in the meantime, and we should continue to think about how to use them. But realistically, if you think about, say, the optimization example, to do a complicated fully connected model, we could do that up to about 16 qubits, and past 16 qubits, it wasn't really working. But to do a industrially relevant optimization problem, you'll probably need a high degree of connectivity and hundreds, if not thousands of bits. And it's almost inconceivable to me that we'd be able to scale to that regime without some sort of error mitigation. So there's clearly still a long ways to go here. And with that, I just want to thank the team. These projects were collaborations with a very large number of people. I want to especially thank Nick Rubin and Matt Harrigan, who played very major leading roles in the design and execution of the Hartree-Fock and QAOA experiments, as well as Vadim Smeliansky and his team for helping us with the calibration and control of the device, and also a very large and amazing hardware effort, which is, there's so many people involved, it doesn't really even make sense to single a few of them out. But with that, I'm ready to take some questions.
Okay, so thank you for your very interesting talk. So we have a number of questions. So first, let's ask, so for your quantum chemistry experiments, you did this up to 12 qubits, whereas you have more qubits, physical qubits available in your processor. So what limits you to that number? Is that due to the accumulation of the errors, or is because you have an impressive error per gate, like 99.5%, right? So even for that, you mentioned you still need to do error mitigation for 6 qubits. You need to do error mitigation already. So the error accumulates pretty fast there. Or?
Yeah, well, one thing I want to emphasize is that quantum chemistry is an application that demands especially high precision, because otherwise you could do these things very easy. Classically, of course, our experiment Hartree-Fock is tractable, but we're sort of thinking about building blocks that would scale to correlated models where the point is to get high accuracy. So for example, the paper that our team put out on Sunday night, it was about simulating the Hubbard model. We did well over 20 qubits for that, and we did well over 600 2-qubit gates and ended up getting quite good results. For the chemistry experiment, we certainly could have gone to larger sizes, but we would have had errors that on a chemical scale would have been quite large. So for example, our ability to discriminate the chemical reaction mechanisms requires a certain accuracy. And if you don't reach that accuracy, you're going to resolve the mechanism incorrectly. And so we stopped at about the level where the methods that we had pulled together were still giving us this standard of chemical accuracy, which is in chemist units, we try to get 1 kcal per mole of accuracy, because that's roughly the air and the energy such that you will miscalculate the rate of a chemical reaction by about a factor of 10 at room temperature, because the rates of chemical reactions are exponentially sensitive to changes in the energy surface. So if you start to have more air than that, it's sort of questionable whether this will really help you predict mechanisms.
Okay, thank you. So it's related to this. So I also want to ask, you mentioned several interesting these error mitigation technologies. So I'm wondering how they are scalable. You mentioned this post-selection method. They probably work well for few qubits, or probably even tens or hundreds qubits. But if you really have a very large number of qubits, does the probability goes down exponentially with the number of qubits when you do this post-selection? Also for this purification.
Yeah. So okay. So for example, for the post-selection on particle number, I mean, I don't really think about it as scaling with the number of qubits. Really, the cost of the method is simply you need to repeat the circuit a number of times. That's scaling 1 over the fidelity. And so, and this is true. I mean, that's sort of the best you could hope for if you're not correcting errors. So whenever you're doing error mitigation, this is sort of the ideal limit, is that you only need to repeat things a number of times. That scaling is 1 over the fidelity. However, the fidelity of the circuits is probably decreasing exponentially in the number of gates. And so in this sense, no error mitigation technique is actually asymptotically scalable. If you want something asymptotically scalable, you have to actually correct the errors. It's not enough to just detect them because you're going to get more and more of them. However, for NISQ calculations, the game is really, I think, more about finite numbers. And indeed, if we could push calculations to the regime of 100 qubits or something like that, I think that's kind of the best we can hope for in NISQ, and that I think would be a big success. So ultimately, we do need error correction because you're right, this isn't in an asymptotic sense scalable, but these techniques are still very helpful for this intermediate regime we're in today.
Okay. So we also have a question from the audience, from Braden. So he asks to get a good estimate of this expectation value of these cost functions for your optimization. So how do the number of measurements needed to scale up with this number of qubits?
Yeah, that's a good question. So the way we're performing the measurements here is what you would call shot noise limited. So you're just you're sampling the cost function. And so generically then the number of measurements is scaling like the variance of the cost function divided by the target precision squared. So for example, if we're looking at an optimization problem like the Sherrington-Kirkpatrick model, there's n squared edges in the model, and so you might expect the variance of that cost function to go roughly like n to the 4. And then it's over epsilon squared. So in that case, n to the 4 over epsilon squared, which is a lot of measurements. But I mean, I think that's kind of the essential trade-off you're making with some of these variational algorithms as opposed to something like phase estimation. In phase estimation, you have better scaling. You have scaling that's quadratically better. It would be like the square root of the variance over epsilon. However, you need that cost to be coherent. And in the NISQ era, it's better to trade more circuit repetitions with shorter circuits for one repetition of a very long circuit.
Okay. There's another question from the audience, Binny. So he's wondering whether you are doing quantum error correction for your sycamore processor there, and is there any major obstacle to do quantum error correction with this device?
So realizing the primitives of quantum error correction is well, ultimately Google has a very serious roadmap to building an error corrected quantum computer. That is the objective of our team. And the next milestones that we're excited about working towards are demonstrating sort of the basic primitives of error correction. In particular, we're aiming to do an experiment where we show in the surface code as you increase the code distance, errors are suppressed exponentially. And this is something that we are working on with the Sycamore processor currently. After that, we hope to demonstrate a prototype of a logical qubit. So this is, I would say this is the priority of our hardware effort right now, is working on this. And we hope to be talking more about that.
Okay, thank you very much. Actually, there are more questions, but I guess due to the limit of time, we have to move on. And thank you very much for your exciting talks.